Download this code from codegive.com, link in the description below. Deformable convolutional networks, DCNs, are an extension of traditional convolutional networks that enable the model to learn spatial transformations of the convolutional kernels. This flexibility allows the network to adapt to the shapes and structures of the input objects, which is especially useful in tasks such as object detection and image segmentation. Key concepts. 1. Deformable convolution. Traditional convolution applies a fixed grid of sampling points to the input feature map. In contrast, deformable convolution allows for the sampling points to be adjusted based on learned offsets, enabling the model to focus on important features more effectively. 2. Offsets. The offsets are learned parameters that shift the sampling points of the convolutional kernel. They are generated through additional convolutional layers that output a grid of offsets for each convolutional kernel. 3. Modulation. Additionally, DCNs can include a modulation mechanism to scale the contributions of different sampling points, allowing the network to weigh the importance of each point dynamically. Structure of a deformable convolutional layer. The architecture of a deformable convolutional layer can be broken down into the following steps. 1. Compute offsets. Use a small convolutional layer to generate offsets for each position in the input feature map. 2. Apply deformable convolution. Use these offsets to sample the input feature map at non-grid positions. 3. Modulate. Optional. Optionally apply a modulation factor to scale the contributions of the sampled points. Code example. Below is an example implementation of a simple deformable convolutional layer using PyTorch. Note that PyTorch does not have built-in support for deformable convolutions, but you can find libraries like TorchVision or implement them manually. You can also use the DCN v2 implementation available in the TorchVision library. Step 1. Install required libraries. Step 2. Implement deformable convolution. Here's a simple way to implement a deformable convolution layer in PyTorch. Explanation. 1. Initialization. We define a deformable conv2d class inheriting from nn.module. In the constructor, we initialize a regular convolution layer and another convolution layer to compute the offsets. 2. Forward pass. In the forward method, we first calculate the offsets by passing the input through the offset_conv. Then we call the deformable_conv method, which would implement the actual sampling logic. 3. Deformable logic. The actual deformation logic is not implemented in this simple example. Implementing the actual sampling based on offsets requires a more complex setup, often involving interpolation. Conclusion. Deformable convolutional networks enhance the ability of CNNs to model complex, non-rigid shapes by allowing the convolution operations to adaptively sample input features. This technique leads to improved performance in various computer vision tasks. For practical implementations, consider using existing libraries that provide optimized versions of deformable convolution layers, such as the TorchVision library or other deep learning frameworks that support DCNs.